Thanks to the organizers for this great honor. We'll talk about graph orientations and linear extensions. So the main object of the talk are the acyclic orientations of a simple and directed graph, which are the orientations of its edges where you don't have reduced directed cycles. I like to think about acyclic orientations as coming from labelings of vertices with the numbers from 1 up to n, where n is the number of vertices. But you can also use any proper coloring to orient the edges in a acyclic way. All acyclic orientations of G can be obtained in this way. Now, any given acyclic orientation uses a partial order on vertices if you take transitive closure of the orientation, and a linear extension of each of these posits recovers the corresponding orientation as in numeral I. So the main problem of the talk is the following. Given a simple graph, as I said, each acyclic orientation induces a partial order on the vertices. And the question is, which of these posits has the maximum number of linear extensions? Or equivalently, if you use one of these objective labelings of B, if you pick one of them uniformly at random, then this is the same as asking what is the most likely acyclic orientation of G. We're going to call this the main problem for G, and the combinatorial statistic of interest here, namely the maximum number of linear extensions, will be denoted by R epsilon of G. So we expect this problem to be hard, in particular since counting the number of linear extensions of an arbitrary concept is known to be sharply contained, the classic result of Draghill and Winkler. Now, as a warm-up example, we have the case of bipartite graphs and odd cycles. So for these families of graphs, we were able to find a simple combinatorial algorithm to provide the answer. So for example, in the case of bipartite graphs, well, before I should say that I'm actually always going to assume that my graphs are connected, since disconnected cases are just a simple extension of the connected case, and it's going to be much simpler to describe the results. So for a connected bipartite graph, the solutions, the optimal orientations are the most natural ones that you can think of, which are the two orientations where you have the two sides of the bipartition and you orient the edges from one side to the other side. So there are two. And the idea of this algorithmic proof is to start with an arbitrary acyclic orientation and a linear extension of the acyclic orientation. So I'm actually identifying the acyclic orientations with the posits that they induce, and then to try to transform injectively the linear extension into a labeling in which you don't have induced directed two paths. So I start, for example, here with this arbitrary acyclic orientation, and I want to map the linear extension to a linear extension of this optimal orientation here. And the idea is very simple. At each step in the algorithm, you basically color with blue the edges that are incorrectly obtained. Then you look at the labels of the vertices adjacent to those edges. You collect those labels in a set, B, and you do the following. If you look at the top level, you select the minimal element. If you look at the bottom element, you select the maximal element, and then you switch those two. And you keep doing that, and that's the algorithm that works. And a similar idea works for odd cycles. The only difference is that, of course, in any cyclic orientation of an odd cycle, you always need to have at least one directed two path. And then what you do is you fix one of those two paths, and then you work with the rest of the graph, as in the bipartite case. Now, Stakowiak had obtained this result for bipartite graphs using poset theory. And we're going to talk about this more later, since we're going to extend his idea. So the problem with these combinatorial algorithms for general graphs is that they're very difficult to find. So we wanted to find some connection of this problem to known theory. And we were able to do so. We were able to connect our problem with the geometry of certain polytopes that I'm sure are well known to most of us, and to basic poset theory. So I'm going to use these conventions that I think are usual for us. So for the geometric part, I'm going to be thinking about these two famous posets defined by Stanley, the order polytope and the chain polytope associated to a poset. So these are both subpolytopes of the n-dimensional cube. The order polytope is described basically by having the coordinates respect the order imposed by the polytope. The chain polytope is defined in a sort of similar way, where you require that the sum of the elements indexed by chains of your poset is bounded above by 1. Now, understanding the order polytope is slightly easier than understanding the chain polytope, and Stanley defined this transfer map phi to try to transfer properties of the order polytope to properties of the chain polytope. So the transfer map is defined in this way, and the main theorem of Stanley is linear extensions of a poset P give a triangulation of the order polytope, where the synthesis have equal volume 1 over n factorial, n is the ground set, n is the ground set of the poset, the number of elements in the poset. And so the volume of the order polytope is the number of linear extensions of the poset divided by n factorial. And then making use of phi, realizing that phi is a continuous bijective map, which is to be restricted to the synthesis of the triangulation of the order polytope. You see that it's linear and unimodular, so the chain polytope has the same volume. Now, the analogous object in the graph world to the chain polytope is probably the stable polytope of the graph. So given a graph G on n vertices n, the stable polytope is the full dimensional polytope in Rn, which is obtained as the convex whole of all vectors is of I, where I is an independent or stable set of your graph. Now, a couple of observations about these polytopes. The vertices of the order polytope are given by indicator vectors of order filters of the poset. Similarly, the vertices of the chain polytope are given by the anti-chains of the poset. And because of this, actually the main problem for G is equivalent to finding the chain polytope of maximal volume contained in the stable polytope of G. Basically what's happening is that when you run over all the acyclic orientations of a graph G, you'll observe that all the chain polytopes of the induced posets are contained in the stable polytope of the graph, and you want to find the one that has maximal volume. Phi is doing what it's supposed to do, connecting these vertices of the chain polytope and the order polytope. Another thing that I should mention is that the order polytope, again, as you run over all the acyclic orientations of a graph, gives you a subdivision of the n-dimensional hybrid. So the same is not true for the chain polytope, which is out there. So it's an example of Stanley's theory for a very simple two-path graph here, where I show the subdivision given by the order polytopes. There are 4 of them, 4 acyclic orientations. And outside, I present the corresponding chain polytopes, corresponding to the closest order polytope via the transfer map. Now, the hyperplanes that I depict here are actually the hyperplanes of the graphical arrangement, and I'll talk about these later, since it will be also important. So, if you think about the connection between the stable polytope and the chain polytopes, you probably realize that the natural family of graphs to consider this problem are comparability graphs. So, I'll remind you, so comparability graphs are graphs for which there exists a partial order on the vertices, in which 2 different vertices are connected if and only if they're comparable in the partial order. And all induced acyclic orientations of the graph induced by such posets are called transitive orientations of G. So these are very special orientations for comparability graphs. So, comparability graphs are important examples of perfect graphs, and they contain a subclass, these many families of graphs that are common to algebraic combinatorics. And there are a couple of motivations, of course. One is poset theory, the other one is perfect graph theory. And a more recent one is actually problems in data mining, in particular problems where you have to perform some correlation analysis and you want to infer causality relations. In fact, this is closely connected to the main problem for G, as you can imagine. So, some key observations about comparability graphs. So the number of transitive orientations of G depends on the modular decomposition of the graph, which is a concept introduced by Galay in the 60s in a very beautiful paper that has only been recently translated to English. There are at least two, for any given comparability graphs, two transitive orientations. Of course, if you have one transitive orientation, you can take the dual, which is basically inverting all the orientations of the edges. But you have at least two. You can have more. And secondly, if you have a comparability graph and if a poset P is obtained from an acyclic orientation of your graph, then the chain polytope is actually equal to the stable polytope, precisely where P is transitive. So as a consequence, you can see something like this. So the number of linear extensions is a comparability variable. So Stanley had also realized this and mentioned this in his paper. So the first main theory that I'd like to present is the solution to the problem for the case of comparability graphs. So when G is a comparability graph, the acyclic orientations of G that maximize the number of linear extensions are precisely the transitive orientations of G. And, there's a very simple geometrical proof of this fact. If you think about any other non-transitive acyclic orientation, well, that induces a poset whose set of anti-chains is strictly contained in the set of independent sets of the graph. And therefore, this gives us strict containment of chain polytopes. And in connection with number 2 here, that's exactly what we want. Now, we also have another poset theoretical proof, which is based on these recurrences for the number of linear extensions. So these two recurrences had actually been obtained long ago by Stanley, Edelman, and Heavy. We have obtained them again using a different technique. So they use promotional evacuation theory. We're going to connect these to network flows. And the statement of the result is as follows. If you have partial order P on ground set N, and if there is an anti-chain of P, then the number of linear extensions of your poset satisfies this inequality, where P minus I denotes the subposet of P on the set of elements N minus I. And similarly, if this is a cut set, remember that a cut set is a set of the elements of your poset in which, such that every maximal chain of your poset intersects your set. If you have a cut set of P, then the number of linear extensions satisfies the reverse inequality. And there's also some equality statement here, which I'll actually present an example of what I did for this theorem. So the idea is to find a recursive approach that resembles the classic recursion to compute the chromatic polynomials, in which you consider edge contractions and deletions. So actually the edge contraction is the one that works here. And if you start doing these pictures, you realize that something nice happens. So
I'm sorry, I've lost track of what you're trying to prove.
So I'm trying to prove that these recurrences are satisfied for the number of linear extensions. So if you have for example here, so yeah, I'll only show an example of how this works. So we have a Hasse diagram of a poset on 5 elements, which has 8 linear extensions. Then we produce this diagram here, which is constructed as follows. So I have added a 1 element and a 0 element to the poset. And you can also see these green numbers that are counting certain things from this list. So in particular, if you look at the number between 4 and 3, so that number is 4, and it's actually the number of linear extensions in this list in which 3 and 4 are consecutive. And actually 4 happens after 3. So there's these first 2 guys, and I guess the last 2. And what you realize is that everything that goes in to a vertex is equal to everything that goes out. So basically you have a network flow here, and then of course you can exploit these to prove these recurrences. It's actually the reason why you end up talking about anti-chains and constants. So And from there, we can use induction to get a second proof of the theory. Now, I should say that Stakowiak had actually resolved the cases by part-time graphs using an analogous technique. Basically, he was using that minimal and maximal elements of a poset and anti-chain concepts, and doing the same induction, which was actually an inspiration for this result. And then we can modify a little bit this theorem to get the result for other families of graphs, including odd cycles and other very pathological examples that I'm not going to talk about. Now, changing the scope to enumeration of bar epsilon of G, first we were able to obtain this result for comparability graphs. Perhaps more importantly, for general simple graphs, you obtain this corollary from the proof of this proposition. And it says the following: if you have a graph G with chromatic number K, and G has n vertices, then variety of G is greater than or equal to n factorial divided by K, n minus K times K factorial. And when we saw this number, we tried to think about the case when G is a random graph. And I'll talk about that right now. So before, an upper bound for bar epsilon of G is given by the number of acyclic orientations of the complement of the graph. It's a very strange result, in my opinion. But it's the only upper bound that we were able to find for general graphs. So we tried to jump to the case of random graphs, trying to understand how this statistic behaves in general. But, I mean, we didn't expect to obtain any interesting result because this statistic belongs to a world of exponential statistics like this number here, the number of acyclic orientations, that are not even hard to compute but also hard to approximate. So we decided to take the logarithm in base 2 of this number, and this is what we are going to study for the random graph case. So in particular, I want to know if there are tight concentration results for this statistic. And it turns out there is something. So if G is distributed as G and P, remember that this is a random graph on n vertices where you select each edge with probability P. P is any number between 0 and 1. And if you define P to be equal to 1 over 1 minus P, then almost surely the statistic of that graph is asymptotically equal to the expected value of the statistic, which is asymptotically equal to this number right here. So I think I'll not have time to discuss the proof. And as a corollary, an interesting corollary of this is that you can obtain an exponential approximation for the volume of a stable polytope of a graph, which is an interesting result because actually describing with inequalities the stable polytope is also a difficult problem in general. Now we want to connect this problem to more common optimization, and before that we need to consider the graphical arrangement of the graph. So I'm sure I don't need to actually introduce this. I think everyone knows what the graphical arrangement of a graph is. A slightly more unknown object is the graphical sonotopology, which is simply the combinatorial dual in the graphical arrangement, and is defined usually like this: a Minkowski sum of line segments coming from the edges of the graph. Now, regions of the graphical arrangement of a graph are in bijection with acyclic orientations of G. So this is why we care about graphical arrangement. And therefore, also the vertices of the graphical sonotone correspond to acyclic orientations. In order to make the connection precise, we made use of this definition of Pleibens and Schwarz. So if you have a central hyperplane arrangement H in Rn, the fractional volume of a region of the hyperplane arrangement is basically the fraction of volume of the unit ball that lies in that particular region. And it's very simple to obtain this result, right? So the volume of a region corresponding to a given acyclic orientation of a graph, region of the hyperplane arrangement of the graphical arrangement is equal to the number of linear extensions of the poset induced by the acyclic orientation divided by the factorial. This is exactly what we're trying to study. So this still seems a bit hopeless to study, so we tried to see if there was a way to connect also the graphical sonotone to this problem. And we propose to do this by looking at the Euclidean norms of the vertices of the graphical sonotone. And there is in particular this result. So if you have a simple graph, G, and a cyclic orientation of its edges, then you select the vertex X corresponding to a given acyclic orientation, then that vertex is coordinate-wise described like this, where these numbers are computed in the orientation. And furthermore, 1/2 times the squared Euclidean norm of your vertex is actually counting some combinatorial patterns in the orientation. So it's counting the number of edges plus the number of triangles plus the number of these three guys here that, I should say that dashed lines means that you don't have the edge, right, originally in the graph. So I'm actually coloring these two guys with blue because they do not depend on the specific choice of orientation, but the red guys do. So they depend on the choice of orientation. And you can imagine that if you try to maximize this quantity, you end up minimizing this guy. So you're basically, in a way, minimizing the number of comparable pairs of the orientation. And intuitively has to do with maximizing the number of linear extensions of the post. So, from this observation, we can actually write very concrete quadratic programs to model this situation. So, if you have a simple graph G, and we have a set of edges E, which are ordered, then you can choose any orientation for the graph, and we let Q be the corresponding n times n incidence matrix, then we can write down these two quadratic programs. The first one is problem P1, where this is like edge space. But you can also consider, you can change the order of the Q's, and you get the vertex problem, which turns out to be something involving the Laplacian of the graph. Now, problem 1 actually solves the maximal norm vertex of the graphical sonotone. So the problem that I was describing in the previous line. And problem 2 solves the max code for G. This is actually well known before. The problem 2 solves max code. And just because of this, and because of this result that counts certain combinatorial patterns, and the previous result, you can infer from this that if G is a comparability graph or an odd-cycle, then actually problem P1 solves the main problem for G. But this is optimization over the hypercube. This is expected to be hard in general. So we tried a mutual relaxation of both problems. And we did that by considering the optimization over the sphere. And then we can basically focus on this form, which is simpler. And you might know that this is actually just asking to describe the eigenspace of the Laplacian corresponding to the largest eigenvalue. And basically from there, we started to study this in detail, which I'm not going to have time to discuss this in detail, but very roughly, the theorem says that if you actually use the eigenvectors of this eigenspace corresponding to the largest eigenvalue of the Laplacian, and if you put those numbers on the vertices as labels, then you can produce a number of orientations of your graph. And you will see that you will obtain actually exactly Galois modular decomposition theory for comparability graphs, which is something I I really like because I really like this paper. And there's even more than just the case of comparability graphs, but I'll not have time to talk about this. So for general simple graph, there's something similar that actually holds. Okay, that's it. Thank you.
Any questions for Benjamin?
So what your second motivating statement, it was a random statement. You're trying to choose what, a random, I forget which way around. You're trying to use random labeling and you want to see what flow says, skips, or the other way around?
I think about
Yeah, slide one. Perhaps two, I don't know. Yeah, problem B. Uniform the random.
yeah, if you have n vertices, then you basically consider.
So you want to know what is the mode, basically.
Yeah.
So, but can you say anything more about this distribution? It seems like it's interesting to push uniform distribution through your. Can you say anything more other than what is the mode?
Oh, you mean for this uniform distribution or
Yeah.
in general?
Not to push the most likely
Well,
acyclic orientation. What
actually-
else can you say about the distribution of acyclic orientation?
So I actually didn't consider anything else different to the uniform distribution. If
No,
that's-
say
if
keep
that's-
uniform distribution, but what else can you say about the acyclic orientation? About the distribution of it? With heavy tails?
Oh, I guess I can. Yeah, I can't say much more than. what it is.
Good answer.
Yeah, it's a
Any-
difficult question.
Any other quick questions? All right, the next talk will be in 2 minutes, so let's thank Benjamin again.